For homework homework 4, part A, we're going to be starting with our non-steady state solution for our changing height of our tank level, which is our cross-sectional area times the change in height is equal to our flow rate coming in minus what's going out. So our alpha times square root of h, our alpha is just going to be the 2g square root times our a out. So we replace this with alpha to simplify things in this scenario, and we still have our h to the 1/2 for square root of h. So now we'll use our deviation variables in order to linearize this solution and eventually use our transfer function to get a linear approximation of our exact solution. So our a times dh dt is going to be equal to our q minus alpha multiplied by the square root of our h bar, so our steady state h condition, plus we will have our derivative of this, so 1 over 2 square root of h bar multiplied by our steady state condition minus what we're at now, so h. And it's important to note that our deviation variable h prime is equal to h bar minus h, and our q prime will be q bar minus q. So now at a point where our dh dt is equal to 0, we know this will be equal to 0 is q bar minus alpha times square root h bar plus 1 over 2 square root h bar. Then again, h bar minus our h, but since we're at our steady state condition, we know that our h is going to be h bar, which means this will be equal to 0. So if we subtract these two equations from each other, we get our cross-sectional area, change in height with respect to time, is equal to our q bar minus q minus alpha multiplied by our 1 over 2 square root of h bar times h minus h. So now we can substitute in our deviation variables, giving us a dh dt is equal to our q prime minus alpha over 2h bar times h prime. So now, using our Laplace transforms, we know that the Laplace transform of dh dt L is equal to big H times S, and then our q prime L is equal to big Q, and our big L of our H prime is just big H. So that gives us ASH equals big Q minus alpha over 2 square root H bar times big H. Moving this over and pulling out our H, we get our H times AS plus alpha over 2 square root H bar is equal to Q. And then isolating our H gives us big H is equal to 1 over AS plus alpha 2 H bar times Q. It's important to also note that our first order transfer function is going to be equal to, or not equal to, but it is k over tau s plus 1. So in this situation, what's on top is going to be our k, and then we need to get this into the form of tau plus 1. So to do that, we divide across by our alpha over 2 square root of h bar, giving us our h is equal to alpha over 2h bar over a times alpha 2h bar times s plus 1 multiplied by q. Whoops, since we divided across, these are all switched, so it's 2h bar over alpha, and then the same thing down here, giving us a2 times square root h bar over alpha. So this is now equal to our tau, this is equal to our k, and we have our 1 here. So now we have our big H is equal to that times q. So what we have now is our deviation variable. So we reverse the transfer function, giving us our h prime, or in this case, our h prime, yeah. So that is equal to 1 minus the exponential of, this needs to be multiplied by, so this is multiplied by our q, which is outside, just a variable, multiplied by our k times the exponential of our time divided by our tau. And we know our deviation variable is just equal to our h minus h bar. So what we get is our h is equal to our h bar plus 1 minus q times k times e to the minus time over tau. And that is how we will linearly approximate our changing height. Okay. For the next part of homework, for part A, we're going to be comparing our linearized transfer function solution to our exact solution. And what we're starting with is our givens from the problem statement and our template. So the first thing we need is our initial height, which is going to be equal to our q0 divided by alpha. And this is going to be squared. We then need our k for our transfer function solution, which is going to be equal to 2 times np dot square root of our h0, and this is going to be divided by our alpha. We then need our tau, which is going to be equal to our cross-sectional area times our k. And lastly, our big Q, which is going to be equal to our Q minus our Q0. So now we'll get our exact solution. So our right-hand side, we'll define right-hand side, a function of time height. And this is going to give us our dH, which is going to be equal to our Q minus our alpha times np square root of our h, which is all going to be divided by our cross-sectional area. And we just want this to return our dH. So next, we'll define our time. So 500 seconds, our t-plot, which will be np linspace from 0 t end. We want 100 points. Then we will get our exact solution, so our result is equal to solve IVP of our function from 0 to t end. T end, our initial height, h0, method, rad u, and then dense output is equal to true in order to evaluate it at each given time. So then our h's will be our res.sol of our t-plot and the first value in this. So we have that, and then we also want to do our linearized solution, which is going to be, we'll call this hlin, and this is going to be equal to our h0 plus our q multiplied by k, and this is multiplied by 1 minus np exp of minus t-plot, our time, divided by tau, and then we will just plot these out. So our figure is equal to make subplots, and then fig dot add scatter. We want our x to be our t-plot, our y to be our h's, and our name for this is our exact solution. It's not how you spell exact. I'm struggling to spell exact. Fig dot add scatter. Our x's again, t-plot. Our y this time will be our h linear solution. Our name for this will be linear. So we'll see what this is. Okay, what is wrong about this? Well, I changed nothing and now it works. Okay, so as you can see that our linear approximation and our exact solution are fairly similar, and as we are to take down time steps or increase the amount of times we take a linear approximation, our solution will approach closer to our exact solution. Okay, so you can see that, I guess if we do this, we'll do 51, so this should be a little further away, and then if we make it, let's say 500, it should be even closer. 1.2